So use cases, we actually need to think about where we be using industrial AI, where should you be using it, and what are some specific use cases? So where could you be using industrial AI? In theory, all you need is something industrial and a bit of data in a short way. But putting that into dot points, if there's an industrial setting or industrial operations that have sensors installed on them, and the data from those sensors is available. So we use sensors as the way to understand the health and opportunity of what industrial systems are actually doing. So what we really need is to be able to get the data from those sensors and be able to build models from that data. In theory, they're the building blocks that allow you to get started. Where should you be using it though? Because there are cases where industrial AI maybe makes more sense than others. And here are some of the things from projects in the last couple of years that stand out. I think it's where you've got industrial operations that you're dealing with multiple objectives that are often in competition with each other, like where you're trying to maximize your production or performance, but also minimize costs. And in a simple way, they can sort of compete. So you've got to potentially, there's a use of industrial AI in helping balance those objectives. Maybe the best dot point here actually is my probably the favorite one is this second one, which is where there is either volume or complexity to the asset. So either you're dealing with a lot of assets for a certain number of engineers, there's just a lot of data. That's just a simple opportunity for industrial AIs. There is too much data for any engineer to be able to handle, or at least they need better tools to handle it. Or if it's too complex that it's almost impossible to process the different dynamics or changes in a system as a person without models to help condense that and give us the insights we need. So volume and complexity are quite key. If you've got both, as in you've got a high number of assets and they're kind of in dynamic environments, then you've sort of hit the nail on opportunity for AI. Data intensive, of course, is key. So it really is one of the key things you need is data. To build models that learn asset behaviors, you need to have assets that produce data. So if you are sort of in a position where you're interested in AI, but perhaps an asset has not been online for very long, there are alternatives or ways you can navigate it. But generally speaking, it is for industrial organizations that have significant amounts of operational data. It doesn't have to be structured or organized. Most are kind of messy and varied in quality. That isn't preventative. It's just a factor to consider of what does that means possible, or how do we prioritize different use cases based on what's available. But data is obviously pretty key to data-driven models. Another one is the cost of missed opportunities. This is really important as well. If there is a cost to not detecting a certain dynamic event is happening, and that can cause equipment to go offline or fail, or anything that's associated with basically not picking up on opportunities, it's really key to consider where AI could at least cast an eye over every single data point that's flowing from your sensors. That is a valuable opportunity to consider AI for, is preventing missed opportunities that have a cost to the business that may not even be getting captured. And also where you've got limited resources. If you don't have the ability to hire 10 times the number of engineers you have today, but you want to become 10 times more effective as a team, you can look at technologies that help better scale your resources. So it really is where you've got limited engineering time and a lot of data and complex systems. That's where you could be looking at using industrial AI. So getting into, I guess, specific use cases, where does it make sense in an operational world? Now, we've just put in here the three things we talked about a little earlier about it's important if you want to detect, predict, and optimize. So if you can fill in the blank after any of those words in relation to the work you do, I'd like to better detect X, or I'd like to better predict when Y is going to happen, or I really need to optimize Z in the work that I'm doing. You're already on the right track. We've just added in control as well, as in that we actually see an opportunity for AI in helping close the loop in the work that we do as engineers, not to replace it, but just augment and take care of more of the manual nitty-gritty configuration tasks that have burdened engineers for so long. So long story short is we've just tacked on control in our own definition of where we see the sort of four things to think about, like where do I need to better control a certain component, a control systems perhaps not performing very well, you've got the opportunity to consider it for that. But in terms of then thinking about what are those, so detect, predict, optimize, control, they're potentially a little still vague. So what does it mean in terms of actually utilizing those 4 keywords in actual engineering tasks? What are things that engineers are actually doing from a Monday to a Friday that they could be benefiting from industrial AI? The first one is in real-time monitoring. Simply put, casting an eye, as we mentioned earlier, over every single data point that's coming out of an industrial system, making sure that's actually flowing through models that have the ability to check and help prioritize insights from those models based on a number of different detection or prediction modeling systems. That all condenses into simple oversight of our assets. It also can help not only with oversight, so we can pick up on earlier identification of any issues or problems. We can also use it to grow our performance with more advanced optimization capabilities. So we can actually build AI into tools that perform dynamic optimization of assets, which basically means that they are not being set up with a very, very specific set of rules to go and implement. We are describing what some of the objectives of our operation are. We want to optimize production and we want to minimize cost. And we find ways to build those into dynamic optimization tools that engineers can use. The other capability is not only to help you with more advanced optimization, but actually thinking about where that can be used. And that can be used directly in smarter control systems. So you can actually set up so that you're not only, let's say, getting recommendations on, hey, this system could be further optimized, you could actually link that into a control system so it's actually able to look at that set point recommendation and go and action it. And what you can then do as an engineer is set that up to run an hour before you come into work. And then when you come into work, instead of having to look at 100 tasks for the day, the AI system's taking care of, let's say, 80 and has said, given you sort of performance insights on what it's done and why. And then you've got a subset of things that you need to check. You need to maybe cast an eye over the AI system to make sure it's performing as you like and make any subtle configuration adjustments as you need. But ultimately, this is about thinking about not creating more and more work for engineers with more insights, more predictions. We really want to make sure that they're actually helping reduce the workload of engineers. And another application of that is going around now to the maintenance and intervention space, looking at ways that you might have heard the phrase predictive maintenance, and that's certainly pretty key to an industrial AI use case. Essentially looking at where AI can help you anticipate events. So how can you use industrial AI systems to anticipate where there is a certain failure potentially going to happen, and what do you want to do with that kind of prediction, and how do you want to build that into a more proactive approach to maintaining and intervening on systems? So we've seen AI systems that can help you, give you insights on, well, recommendations on where you should look at a maintenance activity on a certain asset, and also where you might want to look at an intervention activity on a certain asset, which we're defining more as like, where have you seen signs of degradation that are minor and could be fixed, or major and actually pose a threat to the performance of the overall asset, and you might want to actually go out and repair or replace a piece of equipment. So it's all about trying to leverage AI to distinguish between where should we go forward and invest in maintenance versus intervention. The other thing you can do is look at opportunities in forecasting. So one of the challenges with forecasting, of course, is keeping them up to date and maintained. And if you've got a forecast that you need to, let's say, readjust or change because you operate a dynamic asset and things change over time, you can actually use AI to subtly tweak existing knowledge-driven forecasts, but just adjust them slightly in terms of whatever the tuning parameters are in that certain correlation or method. Actually use AI to look at history and say, right, these are the tuning values I would use for that forecast. There are, of course, diverse forecasting methods, time series forecasting methods, which are maybe a little different to using a knowledge or physics-based forecast. But really, it's just about casting an eye over how you're already forecasting and trying to help you tune them so that you don't have to come in every month and adjust a forecast, for example, but you could actually come in and just keep oversight of how it's being adjusted based on what's actually happening, and maybe intervene if you know something's coming that an AI system simply wouldn't know, but based on your sort of asset designs or something that's coming up. So still a role for engineers to play in forecasting, but there's just an opportunity to improve the automated nature of the tweaks to forecasts. And oversight of assets is really important, of course. And one of the major benefits of AI is in just better asset management. So you can actually cast an eye over your equipment, have it applying different insights, and then you can track what those insights are actually leading to. So AI models aren't entirely set and forget. You can still configure them with certain objectives. It's just that those objectives are less burdensome than traditional methods. And so what you want to be able to do as an asset manager or someone looking at the strategic use of AI is be able to see how are different team members using AI to their advantage, how are we not, let's say, becoming over-reliant on them or considering them a replacement to what we're doing, but how do we look at them as an augmentation to what we do and strengthening our ability to optimize systems better and faster. So if you can get insights at an asset management level of what insights are leading to in terms of performance impacts, that's where AI can also help condense and give you insights on how other AI systems are working. So it's all about finding where AI fits into how you already work and not necessarily having to go in and completely deviate from how you work today, but simply looking at within the work we do, what's manual, what steps potentially are already automated, but because they're not very smart, they're causing us extra effort each and every day. So how do we look at these 6 use cases as a bit of a guiding concept to say, in these 6 areas, if any of these are relevant to the industrial operation that we're operating, how could we potentially look at the use of AI in these different use cases?